Okay, let's just review where we are at the moment and where we're going to go from here. So you've seen the biological motivation for neural networks, and we've talked about how to construct them, and you've constructed one yourself, or two, perhaps, if you've done the X-ray task as well. And we've talked about backpropagation, what activation functions are, why they're nonlinear, how to use a loss function, and much, much more. And we also talked about how to build a neural network in Keras, which is the high-level API which is built on top of TensorFlow. And we've covered the basics of a sequential model, which is the most basic model in Keras. And we've also talked about how we can use it for regression and classification purposes. Okay, where now? So now we're going to go in much more depth regarding the choice of optimizers, regularization methods, and some practical guidelines before our final course project. Okay, so typically very deep neural networks experience something called the vanishing exploding gradients. Let's talk about this. So how again does backpropagation update the weight after each training instance? So the weight is updated in proportion to the partial derivative of the error function with respect to the weight. In some cases, this gradient can become exceedingly small, preventing there from being any significant update in the weight. And if you think about this, you can't really change the current value of the weight if you're updating it in terms of its partial derivative with respect to the error function. And if that value is very small, you're not really doing much to the weight in question. So the effect is usually larger for neurons in lower levels of the neural network. And this, of course, means that different levels or different layers are learning at different rates. So in a paper by Glorot and Benguiao, they've pointed out some key suspects, and one of them is the popular logistic sigmoid activation function. And we're going to talk about why, but we'll continue for now. Another one is the standard weight initialization technique, where you would initialize all the weights as random Gaussian with mean 0 and standard deviation 1. This basically results in the variance of the outputs of each layer being greater than the variance of the inputs. And the variance just keeps increasing until it reaches the final layers. So keep in mind that the variance keeps increasing. Let's look at the sigmoid activation function. So if the variance keeps increasing, we're going to start tending towards these values on the extreme, and we're going to start saturating here. And this is what it's called. The function saturates at each extreme, and the gradient here is almost 0. It's not exactly 0, but it's because it's asymptotic, it tends to 0. And if you're updating in proportion to this, if you're updating with almost 0 update, then you're not doing very much to the weights. And the lower layers are most affected because there's much less gradient to propagate back through. And in some cases, the opposite can happen with exploding gradients, but most of the time you'll see vanishing gradients. Okay, choose all that apply. What are the main suspects for the vanishing exploding gradients problem? And these are the answers. Of course, neurons is wrong. Neurons is what the neural network is made of. Xavier initialization, we'll talk about this soon, which partially solves the problem. Convolutional layers, this is just the type of architecture. The main suspects are the typical way we initialize weights and the sigmoid activation function. All right, thank you.